today we will be going over the simulation setup for our centrifugal pump case. Now at this point you must already have flagged your geometry, and you must have say 8 boundaries, and you can just name it and order it just like what I have done in this particular video. So as far as application goes, let's just make sure that general flow is selected, and then we are going to be clicking on material. Now in our case we have selected only liquid simulation, so that means this is just going to be a pure incompressible run. Now ideally in centrifugal pump simulations, cavitation will also occur or might occur. In that case the simulation becomes two-phase. You have water or the working fluid, and you have the gaseous phase, right? So if cavitation needs to be simulated, then you need to have gas simulation. Now we are not going to be doing that because running a centrifugal pump simulation with moving mesh and cavitation can be extremely expensive, and in order for the simulation to run correctly, it can take in a lot of computational time and also memory. So in this particular case we are going to stick with incompressible flow only, and we are going to be doing only a liquid simulation. So let's select that, and let's go to liquid simulation, and then from predefined liquids, what I've already done is I've selected water, which is right here, and I have added it, right? So that's why you see H2O here. And then the next thing that I need to do is I need to go to species, and under liquid I have already clicked on query available list, and H2O has already been added. So I can kind of show you this. I'll just delete this. If you click on query available list, H2O should show up. You can select it and then click OK. Alright, so then let's proceed on to simulation parameters. Now as far as the run is concerned, we are going to be running a transient simulation directly, and we are going to be using incompressible for the liquid flow solver. Now there is an option called compressible liquid, which can be used for liquid flow simulations, but in our case we are going to be using only incompressible. Usually compressible flow liquids are used for really high velocity cases. For example, you have a very high pressure fuel injector, right? In those type of situations, using a compressible liquid flow solver is required. In our case, the velocities in the liquid are not that high, so using the incompressible solver should be good. When you click on OK, you get this question: do you want to load tolerance, relaxation, and piezo defaults? Click on yes, because Converge optimizes the solver settings for different types of applications, and it's better to take advantage of it. As far as the simulation time is concerned, we are basically running it for 0.2 seconds. So how did I come up with this? Well, the impeller in this particular case is spinning at 12,000 degrees per second. I'll let you figure out what that is in RPM. And ideally what you want to do is you want to simulate it at least for 2 rotations, right? 2 impeller rotations, and you can go up to 5 or even 6 rotations to kind of confidently say that the simulation has reached a steady state. Now when I say steady state, I'm still talking about a transient solver. What I mean is, if you run the transient solver long enough, the flow pattern is going to be repeating itself again and again. Thereby the flow reaches a steady state, or at least a pseudo steady state. Alright, so I hope you're not confused with that concept. So moving on, let's just click OK here. Solver parameters we don't have to touch. We can use the default parameters. So let's go to boundary. So at the inlet, what I've done is I've specified total pressure boundary condition. Now if you're working for an oil and gas industry, or you plan to work, typically when you get this type of simulations, you get accurate specifications for boundary condition. So basically here what we are doing is we are specifying the pressure head that's available at the inlet of the pump. Now in this case, I'm assuming a total pressure of 101325, right? Realistically, this value depends on a lot of factors. Especially for large pumps, there is something called as net positive suction head required, which is basically the minimum pressure head that you need at the inlet to kind of prevent cavitation. In our case, we are not simulating the cavitation, so the effect of NPSH will not be seen in our simulation. Alright, so we're going with this particular value. And the other thing that you have to realize here is we are running a purely incompressible flow simulation, right? In an incompressible flow simulation, you are solving only for the pressure gradient. So the absolute value of pressure doesn't matter, right? So depending upon this inlet pressure condition and the outlet mass flow rate, a suitable pressure drop will be calculated by the CFD solver. Okay, so in this particular case, we are just saying that water is our working fluid, and at the outlet, if you see here, I'm providing the mass flow rate. Right now you can see that in this particular case the mass flow rate is pretty high because the impeller diameter is quite huge. It's around 20 centimeters, right? So 156 kg per second. Where do you get this value from? Again, from pump performance data. You cannot guess this particular value because you might prescribe a pressure and mass flow rate combination that's outside the pump performance curve, and it might not work at all. So you need to make sure that you give these values from a pump performance curve. Now for this particular made up pump, the mass flow rate can vary from 120 to roughly 180 kg per second. I've put in a value of 156 because that's kind of in the middle, right? And this corresponds to the RPM at which the impeller is rotating. If you take a look at the intake runner, we are just applying the law of the wall boundary condition here and nothing special. If you look at the shroud, we do the same treatment. If you look at the impeller, this is where we are saying that it's a rotating wall, and we are providing the rotation rate in degrees per second. And notice how it's rotating about the negative z-axis, right? So if you see here, negative z-axis is basically normal to the screen, right? So if you apply the right hand thumb rule, you can basically see that in this particular view, the impeller is going to rotate counterclockwise. All right, so coming back here, you can see that for impeller, impeller sweep and impeller bottom, we have given the same boundary condition because these parts are all connected together. And this is one area where people make a lot of mistake. They accidentally flag impeller sweep or impeller bottom as a wall. So what's happening is that the impeller bottom is staying in place, whereas the impeller is rotating, which causes the deformation of the geometry, and that can lead to intersection errors, which can eventually lead to the case crashing, right? So be very careful when you're setting up simulations where parts are rotating. So finally, we look at the volute. And now if you look at the volute, it's again a wall, right? And we are basically using the law of the wall boundary condition there, and it's all good to go. In our case, we just have one region, and that's being filled with water, and we can just close this guy as well. As far as turbulence model goes, we are using RNG K epsilon. Now in this particular case, we are interested in capturing the pressure drop for the provided mass flow rate. So for that, the RNG K epsilon turbulence model or even the standard K epsilon turbulence model should be good. If we need more information such as the drag on the impeller, then we would have to use the K omega SST turbulence model. Okay, so in this case, I'm just going to click on OK. So let me just enable the bounding box so that you appreciate the size of the geometry. You can see that the bounding box along the x-axis is almost 59 centimeters, 0.59 meters, right? So that's pretty big. And if you want to measure the size of the impeller, this is how you do it in Converge. So what I'm doing is I'm selecting a particular component and I'm using the shortcut key V to hide it, right? So that's how I hid the intake runner and the shroud. I'm going to disable the normals and I'm going to hide the volute as well, and also the outflow. Then I can go to measure and then click on distance, and what I can do is I can just roughly make a measurement. This should be good enough. When I do that, you can see that the distance is 2.82 e minus 1, right? So that's actually 28.2 centimeters. If you have to measure it accurately, then you can go to measure, direction, arc normal, and you can just select 3 points like on the bottom side of the impeller. Oops, let me clear the last point and select this one correctly. Click apply, and there you go. So it's about 23.8 centimeters. That's the diameter of this particular region. All right, so that looks good to me. Now you can see that there is an area where the diameter might be larger than that. Actually, no, I take it back. 23.8 centimeter is the diameter of the impeller, right? So that's basically it. Our case is completely set up. So what we are going to do is we're going to run the simulation. So that's basically it. The case setup is all complete. So let's go to post variable selection, and we'll make sure that turbulent viscosity is selected. You can add y plus if you want to, but I'm not going to do it. So let me just click on OK. As far as output files are concerned, I'm just making sure that I save a lot of 3D post files so that I can do some post processing and I can understand how pressure and velocity are varying throughout the geometry. Okay, so what we are going to do next is we are going to submit a simulation, and we're going to run it, and this simulation is going to take a lot of time, and once we have some results, we will discuss it. All right, with that, I'd like to conclude this video, and I'll see you in the next one. Bye.